semester we used the creepy nurse room with the creepy nurse dolls.
I like the nurse room. So, yeah, because the nursing room is also an option if we really don't like the ICN room. But like Cameron's saying, maybe you've seen like the beds with the little mannequins laying down. Yeah.
Super creepy.
That can be kind of rough. Okay. So actually we did these slides. I'm not going to do all the slides, but just to kind of get a running start at it. I need you to remember that last equality there. And remember that we can take equalities like this and use them as conversion factors. Okay? And then actually your homework today, that's what you did. Okay, so 1 mole of atoms is 6.022 times 10 to the 23rd atoms. Those are the two conversion factors. They are the flip of each other, right? And we did this problem. The first one is a what? Atoms to moles problem. And the second one is a moles to atoms problem. Yep, good deal. It's like deja vu. Okay, so this is a new slide. This is, we didn't talk about this yet. So a mole is 6.022 times 10 to the 23rd of anything. That's what a mole is. And so then a molar mass, I love it because if you're like, well, define molar mass. Okay, it's a mass of 1 mole. It is a mass in grams of 1 mole of anything. Okay, so units of molar mass are grams per 1 mole, or grams per mole. Molar mass. And you might think, well, because we talked about using rice grains, how like a mole is a lot. Okay, so, but as it turns out, if you want 1 mole of atoms, it's not so much. It's quite doable because atoms are so small. So usually it's written grams/mole, grams per mole. But I think it's good to be able to unpack it and basically emphasize that units of grams of the substance are in the numerator and units of moles are in the denominator once you have the number for molar mass. Of course, we can go ahead and use like this little anytime you see anything raised to a negative power, that means it's in the denominator. So raised to the negative first, it's to the first power in the denominator, which is exactly what that is. So another way to think about it, excuse me, when we we're kind of playing around with the concept of a mole and applying it to silly things like hockey pucks, we said that if you had a mole of hockey pucks, it would be equal in mass to the moon. So the molar mass of hockey pucks is the mass of the moon. That's kind of how that works. It's a lot of hockey pucks. So we're going to focus on molar mass for the elements. And each element, like carbon, chromium, lead, each element has their own molar mass. So if you want 1 mole of carbon atoms, you're going to have to weigh a different amount than if you want 1 mole of phosphorus atoms. Okay? It's like a physical, I think it's like a physical property of that element. So for atoms, okay, for different elements, okay, the molar mass of any element is that decimal number. It's the average atomic weight. So the molar mass is the average atomic weight for that element. But we said that in terms of average atomic weight or the synonyms for that, those units are AMUs, the symbol U, okay? So average atomic weight units are AMUs. Now, molar mass units are grams per mole. Grams per mole. But numerically, it's equivalent. Okay? So, for instance, if we pick on carbon, carbon is one that maybe some of you already know the decimal number for. The decimal number is 12.01. So that means a carbon atom weighs, an atom of carbon weighs 12.01 AMUs, okay? And the molar mass, and I abbreviate molar mass, MM, the molar mass of carbon is 12.01 and units are grams per 1 mole. That's the molar mass. Molar mass. My favorite thing is molar mass of magnesium. For some reason, I just love that. Molar mass. 24.31 grams per mole. Okay, so each element, that was carbon, each element has its own molar mass. Each element has shares the same decimal number of its molar mass with its atomic weight. So it's just kind of handy. So if you're a visual person, here are some substances. There's 1 mole of each of these things. So for instance, that looks like 1 mole of copper, 1 mole of sulfur, okay, 1 mole of mercury, Hg, and 1 mole of helium atoms. Okay, so they're different volumes, they're different densities, right? But if we were to, in each of those cases, and we're going to show you how you, of course we can't count those helium atoms, okay? But we're going to show you that if you, well, it's not quite much of a stretch. If you know the mass of that helium, you can know the moles, okay, of helium atoms in there. So we don't count them. We just can't take the time to do that. Here's a picture that also has 1 mole quantities of some elements: sulfur, magnesium, tin, silicon, copper, okay? So the other day we picked on copper, didn't we? We looked at copper. We looked at the different isotopic forms of copper, and we came up with the decimal number for copper. It was like 64 point. What is it? That one I don't have memorized. The decimal number is, 63.55. Okay. 63.55 AMUs is how much a copper atom weighs. Okay. Also then, you know, if this is 1 mole, okay, I know that it's 63.55 grams of copper per 1 mole of copper. Now, I could be more clear with that 63.55 grams over 1 mole. I could be more clear by putting 63.55 grams Cu over 1 mole of Cu. Okay? So it's a physical property of the element. And if you have a periodic table, then you have all of that handy. By the way, you have a homework coming up where you're going to be working with tin. Anybody remember what the symbol for tin is? SN. It is SN. Very good. SN. So molar masses. Molar masses. The units for molar mass are, like we said, grams of the substance per mole, specifically per 1 mole. That's what the units are. So the units of anything can actually tell you how you can use that physical property, in this case molar mass, as a conversion factor to go back and forth between what? Well, to go back and forth between grams of substance, okay, and moles of substance. So molar mass is something that we can work problems going back and forth. If we're given grams, we can get to moles. If we're given moles, we can get to grams. So let's work a couple problems. Again, it's like I said Friday, that the thing in brackets may not necessarily be there. So actually the same problem, when you're reading it in the textbook, it probably will simply say, how many moles is 0.487 grams of calcium? Okay? So right off the bat, we're dealing with, we have to have a periodic table and look up the decimal number for calcium. And when you look it up, it should read 40.08 grams per mole. Or the decimal number will be 40.08. Is that what that one says? Okay. And of course, that means AMUs for how much an atom would weigh. And then that's also grams per mole for how much, what its molar mass is. So when I grade things, sometimes it's easy to grade. If I don't see something like that or like that, written down, working a problem like this, then I know something's amiss. Oh, look. The thing about it is those are set up so we can use them using the factor label method, okay? The factor label method is here to stay. Some of you wonder, and some of you may not wonder, why chemistry teachers and your textbook, Petrucci, really emphasizes this way of working problems. It just makes life easier. You know, in physical science, if you can use factor label, you can get anywhere. So let's go ahead and work this problem. The first term is going to be the thing we want to convert. So it's going to be that 0.487 grams calcium over 1. 0.487 grams calcium over 1. Now, I will tell on myself, I will say that sometimes when I'm working a problem like this, if I only have one element, in this case, the only element involved in the problem is calcium, I will get kind of sloppy and just not say what the element is. But if we want grams to cancel, do you see where we're going to use what I call the flipped version of molar mass? So since we want grams of calcium to cancel, if we put 1 mole of calcium over 40.08 grams of calcium, okay, again, it's back to the factoring out labels or units that cancel. And we're left with units of moles of calcium, and we're done. I know we didn't divide it out yet, but we're essentially done because the units work. Okay, so looks like 3 significant figures. Okay, so did you get this? Yay! So remember, if we need 3 significant figures, okay, although this 0, well, both of them, but especially this 0 is important to give magnitude, it doesn't count for being a significant figure. So we have 3 significant figures. That's it. Let's do another one. So this was what? A mass to moles problem. Now, of course, the other one's going to be a moles to mass problem. And now we're dealing with boron instead of calcium. So we're going to need the periodic table. Look up what boron is, the decimal number. And so remember, usually when it's written, you won't see this last word atoms here. So it'd say what mass in grams is 1.33 moles of boron. It's just understood of boron atoms. So for boron, the decimal number is 10.81. So remember that decimal number counts as how much a boron atom weighs in AMUs. That decimal number also counts for the molar mass of the element boron. So of course, we can kind of come up with these three ways to look at the molar mass of boron. We can say there are 10.81 grams of boron in 1 mole of boron. We can say in 1 mole of boron, there would be 10.81 grams of boron. We can flatten it out and say, for boron, 10.81 grams is equal to 1 mole for boron. All right. What did the one termite say to the other termite? Boron. Sorry. Okay, so the first term is always going to be the thing you want to convert. So it won't be your molar mass. So you're going to start with 1.33 moles of boron over 1. Since you want moles of boron to cancel, you use the unflipped version of boron, which is that 10.81 grams of boron over 1 mole of boron. And the only reason you're doing this now is so moles of boron will cancel. You're left with units of grams of boron, and your units are great. And if your units are great, you must have it set up right, unless you lied about your units, which happens. So 3 significant figures, 14.4 grams of boron. Is that right? And that leads us to the assignment slide. Okay. Now, just to make sure we're all on the same page, do not take these lightly. Part of you, the reason for doing homework, and I'm not saying you guys are, right? Part of the reason for doing homework is that you know what I expect, for instance, on a test, okay? you're going to see these exact same instructions for your problems on your test. Okay? So show all of your work. You've got to use the factor label method. You know, feel free to refer to your in-class lecture slides. And then it says you need to make sure that you round according to the correct number of significant figures. I will again tell on myself a little bit. For these first unit exams, I'm going to be a stickler about sig figs, and I usually try to catch them in your homework if you didn't round correctly. I think I was a little bit quick on grading some of your lab write-ups, so you know, feel free to, if you have any questions about how you rounded and I didn't catch it, let me know. But for your, what was I going to say? For your tests, okay, that you're going to have a week from Thursday, you will miss points if you don't round correctly. My physical science class this semester, they can round however they want to. We kind of got the ballpark thing going. Okay, but you guys, you have to round correctly. So let's take a look at those. And I already pushed them out on Twitter feed. I was also with it. Okay, sort of. What numbers were they?
They are 257, 58, 59, and 60.
I moved my stuff around. Phew. I was like, dang, that's a lot of work. Well, so anyway, these two problems are kind of similar. And see, the thing is, some of you don't need these hints. Okay, so you might just want to work it and then see if you need the hints. But I gave it the hints for A. That's a mass to moles problem. That's pretty straightforward. Okay. For B, basically, you're going after chromium atoms. You're given the mass of chromium. Okay. So if you're going after atoms, you're going to have to use Avogadro's number, kind of like we talked about on Friday. Okay. So notice you're starting with kilograms instead of grams. So got to fix that right off the bat. Go to grams. Okay. Once you're in grams, you can use the molar mass of chromium to get to moles. Once you have moles, then you can use Avogadro's number to get to atoms. So for C, you're after grams of AU is gold, okay, from this number of gold atoms. So you're going to go from atoms of gold to moles of gold, okay, and then you're going to use an Avogadro's number. Then you're going to go from moles of gold to mass of gold using the molar mass. So again, you know, some of you guys, you really don't need these hints. I went ahead and told you D. You're going for grams of fluorine. It's kind of fun. You're going for grams of fluorine in one cute little fluorine atom. Okay? There's probably more than one way to skin this cat, but this is how I did it this afternoon. I would go from one fluorine atom to moles of atoms. It's going to be a little tiny little piece of a mole. And once you have moles of fluorine, then you can use the molar mass of fluorine to get to grams of fluorine. So that's how I did it. And again, sometimes in chemistry, there's more than one way to skin the cat. But you always have to use the factor label method, and I catch you on the other side. So for A on 58, it's very similar to B on 57. For B on 58, it's down here. For B on 58, big M means the molar mass. Okay? So in 58B, they gave you the number of the number of atoms in the sample, 2.8 times 10 to the 22nd atoms, okay? And they gave you the mass, okay? So sometimes for this particular problem, I wrote a question mark, what I'm after. Molar mass, what is it? Grams per mole. What do I have? I have grams per atom, okay? I need to fix that from atoms to moles. Okay, and I can't remember, I think I said how you do that. Yeah, I went ahead and even showed you. Basically, you can fix the atoms to moles by using Avogadro's number, 6.022 times 10 to the 23rd atoms in 1 mole. So there's my hint there. That was B. For C, Okay, for C, I can remember some semesters, C really throws people off. It's not meant to, or maybe it is, okay? But if you read C a few times, you'll notice that it's dealing with two things. It's dealing with magnesium and phosphorus. Oops, boy, that's a lot of stuff. Basically, you want the mass of phosphorus that has the same number of atoms in it as magnesium atoms in 44.75 grams of magnesium. Okay, so with that in mind, this actually, equality down here, I picked up out of the problem. I said, how's it set up? Well, you want to have a 1-to-1 relationship between the atoms of phosphorus and the atoms of magnesium. In other words, for every 1 mole of phosphorus, you want to have 1 mole of magnesium atoms. Okay, so then that's my link that I use up there. So with that in mind, you can go from that mass of magnesium to moles of magnesium using magnesium's molar mass. Okay, I love that, magnesium's molar mass. Tomorrow you guys are going to be working with magnesium. I'll try not to laugh, but it does make me laugh. So once you have moles of magnesium, then you're going to skip to moles of phosphorus, knowing that you want them to be the same per the problem. Then you'll have moles of phosphorus, and to get to mass of phosphorus, you need to use phosphorus's molar mass. Not nearly so funny. Okay. These, 59 and 60, look like this. They both deal with mixtures. Sterling silver actually is a mixture of silver and copper. Of interest here is how many copper atoms do you have in a certain mass of sterling silver? Okay, it's a mixture, and since it's a mixture, we're going to deal with weight percent. So one of the things you're going to need to unpack is that 92.5% silver. Well, if it's 92.5% silver, how much of it is, what percent of it is copper? Yep, very good. 7.5. You just got that by difference, didn't you? Perfect. So you're going to need to unpack that. Okay, and we're after copper, so we're going to say there are 7.5 grams of copper in 100 grams of the mixture, sterling silver. Okay, then things kind of fall into place. Do you see where actually I can insert this up here? Okay, put 33.24 grams of sterling silver over 1, and actually I don't even have to flip it, do I? If I insert this up there, my grams of sterling silver will cancel. I'll be left with grams of copper, and I'm on my way. Or you're on your way. Once you get grams of copper, it's not too bad. But remember, to get clear to copper atoms, we're going to go through moles, using the molar mass of copper and then Avogadro's number. 60 is also a mixture. And so for 60, we're dealing with solder, which is actually, remember I told you SN, you'll be using SN, okay? It's a lead-tin alloy mixture. 67% lead, so by difference, 100 minus that would be your percent of tin, okay? So here is the weight percents unpacked. A little bit of a catch to problem number 60, it wants total atoms. Okay, so again, there's more than one way to skin this cat, but basically I went for atoms of lead, okay, and then I went for atoms of tin, and then add them together. So to get atoms of lead first, okay, it looks like this. Okay, we're given the volume of solder, not the mass of solder. So if we're given the volume, we can get to mass, volume to mass, using the density. The density is given as 9.4 grams per centimeter cubed. Okay, so we can get from volume to grams that way. Once you have grams of solder, you're ready to go ahead and insert that weight percent to get from grams of solder to grams of lead. Once you get grams of lead, you can get to moles of lead using its molar mass. Once you have moles of lead, you can get to lead atoms by using Avogadro's number. Okay? So, like I said, there's more than one way to skin this cat. I said do a similar thing for tin using the weight percent for tin. You'll get 10 atoms, okay, and add them together for a total number of atoms. So, any questions? Yeah, that's what I thought. Okay.